is coming.
Sunday, September 9th, 1900, revealed one of the most horrible sights that ever a civilized people looked upon, where 20,000 people lived on the 8th.
Okay, we're going to queue up another video. This is not the amusing one. The one will be coming in just a second. Dave, just let me know when it's ready to go. This will not be.
Say you've been observing Earth's weather using GOES satellites for the past 40 years, and suddenly you realize you need to launch another satellite to keep doing it because it's really important. Naturally, you might think to yourself, great, let's just box up parts from the previous satellites, launch them into space, and let them do their thing. Unfortunately, that's just not how it works. Scientists and engineers are always looking for better ways to improve the weather forecast, and for them, images like this from decades-old satellites just aren't quite up to snuff. Thankfully, scientists and engineers have been busy working with meteorologists to improve things, so they have an idea of what data is needed next. That way, when they launch a new satellite, they're adding to what they've learned before, which means even better weather forecasts for the rest of us. So, when you build a satellite in NOAA's new GOES series, called GOES-R, it naturally sets off a flurry of activity. Because they always want to improve things, engineers might change the satellite platform, upgrade all the instruments, and, because it's meant to improve the forecast, add something totally new that's never been done before, like a new lightning mapper. After months of constructive debates, and probably more than a few late nights, they'll finally come to an agreement. Once everything's been approved, the engineers get to design and put the satellite together. However, even though they've built GOES satellites before, it's not just a matter of pulling out the old designs and bolting everything together. Because there's new science to be done, things have to be redesigned, modified, upgraded, built, tested, retested, tested some more, and finally delivered, so that at the end of the day, it all fits neatly atop a giant rocket. Once all that's finished, the satellite launches into space, the scientists and engineers celebrate, and lots of new data starts coming in that improves the weather forecasts for us here on Earth.
How easy that is. Well, thanks, Dave. I'm going to have to tell my wife, though, I've never been referred to as eye candy so many times in 24 hours, so I have to tell her what a great catch she got 35 years ago. It's a very much an honor to be here today because I'm just a spokesman for an incredibly big and dedicated team who's been working on this program for many, many years. We've got a great cadre of NOAA and NASA civil servants, about a dozen support contractor companies who give us support within the government project office, and then another dozen major contractors who are doing the heavy lifting and building all the components of that. All told, there's probably a few thousand people who've been really dedicated to bringing to this nation the next generation of the geostationary operational environmental satellites. So the team has been working a long time. They're very motivated. A lot of engineers, we get to work on things, but things aren't necessarily always fun. GOES and the mission it supports has got the interest of everyone from the top to the bottom. We bring scientists in to the people actually building the boxes and tell them what it's going to be used for. You can be seeing this on your evening newscast, and they get very excited about it. So we've got a team dedicated to the mission and very excited in delivering this great new capability to the nation. So we've got excitement. So what I hope to do today then is sort of bring and get some of that excitement out to you guys so that as we prepare to launch this new capability, you will do everything you can so that when we put this up in space and turn it on, everybody will know what to use the data for and how to use it and take maximum advantage of these wonderful capabilities. So what I'm going to do today is give a little bit of context for the satellite program, go on to, since I'm the program manager, I got to show all my cool pictures of my little toys, and then go on to probably what you're more interested in is some of the outputs and what we've been able to do in preparation for the data sets. So first of all, let me just say I'm coming from NESDIS, the national, we basically call it the NOAA Satellite Service. So we're a sister agency to the Weather Service. So we provide the basically the satellite observations to support the National Weather Service. While I like to think of the GOES program as the premier program, there's a lot of other satellite programs, the JPSS, the Polar program, is another one. This month, in fact, we're going to be launching Discover, which is a follow-on to the NASA ACE program out at the L1 point for space weather warnings. And then later on this year, we'll be launching JASON, which is a joint US-Europe altimetry program to continue that observational set. So there's a lot of capability at NESDIS, and we do provide these satellite services for the nation. But in addition to just what we provide as NOAA, we work through the World Meteorological Organization Coordination Group for Meteorological Satellites, CGMS, to coordinate all the operational organizations around the world who fly operational satellites so that we share ideas on new frequencies, new instruments, try to get commonality in the data sets, and probably more importantly is back each other up. I know that in the GOES program we've had to do this a couple times in history since I've been at NOAA. First, when we were a little slow in getting the GOES-I done, we had to actually work with EUMETSAT, and they moved over one of their spare satellites over to help us out. And then Japan ran into that similar problem. They had an early failure in theirs, and we moved one of our spares out there. So there is a lot of international collaboration to make sure these data sets are there all the time for when you need them. Looking back at just GOES, the first of the satellites to support weather service came in 1960, the low Earth orbiters. But NASA first flew an experimental geostationary, just put imagery up on the SMS program in 1970. And guys like Rich Knapp up the Hurricane Center and others, when the first time they saw a geostationary picture of a cloud, they said, this has got to go. We got to have this permanently. And very rapidly, by 1975, we put the first GOES up into space. If you look at the history of GOES, there's not been a lot of improvements from a science perspective. Basic imagery, we added some vertical profiling at GOES 4, but we changed the spacecraft a little bit over time. But fundamentally, the instruments and the capability that we originally started with the 70s is still basically what's flying today. So GOES-R really represents an end-to-end complete redo of the entire system for the geostationary program. So this is almost one of those once-in-a-career opportunities to really make your imprint in getting new capability into a satellite system. Even though we are getting the new stuff, I can never forget that our real purpose is to maintain the continuity of the observation. So right now we have GOES 13 and 15 in the operational slots, east and west, and GOES 14 as our on-orbit spare. So really my challenge for my bosses to me is to get GOES-R done by 16, which is a little after GOES 13 would be failed to be the spare. And then the subsequent series to fill that. So we very carefully monitor the satellite on-orbit health and try to time our acquisitions to get keep the constellation healthy. Guess what? We're launching in March of 16. This has been, Kathy, we had to go through, about a year before launch, you have to go, we call it playing launch poker. Everybody who wants to launch sort of sits there and says, well, I'll be done here and here and here. And so we just went through that exercise. The launch manifest, we launch on an Atlas 5, is so busy that there's like 2 launches a month out through the next year and a half. And so if you miss your slot, you sort of get kicked to the end of the line. So it's really an interesting game of saying, having the high confidence that you'll be done and you'll be able to meet your date. The thing I do want to point out is that once we do launch it, we've got about a 6-month checkout period. If you recall on the last chart, normally we'd put in a storage until the east or west capability. We just announced at AMS last week that because of the new capability that we're bringing in on board with GOES-R, that once we finish our 6-month checkup period, make sure all the systems are working, we will continue to leave it on so that nobody misses out on this data set. We just couldn't imagine putting this into storage and just waiting for the old ones to die. So that will be good news because we'll be able to start using these data sets very quickly. And the pressure will be on to get everything checked out as fast as we can. Now, getting a little more detailed into GOES-R, if you're familiar with the current GOES system, basically you have an imaging capability that I know all of you use probably daily. What we're doing is we're dramatically increasing the capability of that imager. I'll get into that. We're adding a new capability. We're adding a lightning mapper for the first time. And we were really getting exciting feedback in terms of potential of that. And we're also expanding a lot of the sensitivity and capability of our space weather instruments. And I'll go through each of these instruments and what their capability is. But like I said before, this is almost a once-in-a-career opportunity to really get changes into the program. In terms of what my job is, I've been handed a task. It's really a requirements-based thing. I get told to do X, Y, and Z for X, Y dollars on these dates. So it's a very prescribed work. I got to build these 4 satellites, get them launched. And I've got a great NOAA NASA team here. We're working out of Goddard. Let's see. So we lost that. Just from the fleet configuration, the current fleet goes east, runs out of 75 west, and goes west out of 135 west. Because the increased data rate of these satellites, we're having to go up to an X-band downlink. And there's conflicts out at 135, so we've had to move over to 137. So that's not a minor difference. But we have the checkout positions in the middle of the country. In terms of the overall architecture, looks a lot like it is today. The 2 satellites on orbit with a spare. The NSOF is our satellite operations facility where we do all of our satellite operations and data processing. We have our command and data acquisition site down at Wallops, Virginia, where we actually pull all the raw data down, process it into what's called a 1B. It's got navigation and geolocation on it. And then we basically ship that out in what today is known as GVAR. We're renaming it as the GOES-R rebroadcast. And that's the product stream that then people make the products over. In terms of what the data availability is, the data processing is all at NSOF. The access to the data will be through the direct broadcast, the GOES-R rebroadcast. We're also putting in a 7-day rolling archive of all of our products. So that will be an internet-based, so you can subscribe or access and bring things out through that. And then we'll have the class, which is our long-term archive of it, so the data will all be available at our data centers. We also have a direct connect to the weather service through AWIPS, so that then they feed through NOAA port to get that as fast, very fast to get the data out to all the forecast offices. The one new thing we are doing this time is we put a full backup capability in for the command and operations out at Fairmont, West Virginia. So that's from our facilities, the new part of the system. Just a quick look at what the satellite looks like, the instruments and their location. Let's see, I guess I can use a cursor here. That's dangerous. Down here at this end, you can see the imager and the lightning mapper on the Earth-facing surface. The SUVI and the Exis, since they're telescopes looking at the sun, we put them right on the yoke of the solar array, figuring that if we're powered up, it's going to be looking at the sun, and that's a pretty safe bet. Then the space environmental, we also have scattered around the north or the upward-facing part of the bus. And then our magnetometer we put way out here on a 10-meter boom, because the magnetometer picks up a lot of electronics if you're too close to the spacecraft. Going into each of the instruments' capability, the Earth pointing, you can see the size of the imager to take high-resolution images from 22,000 miles up is quite a masterful piece of engineering. It's about the size of your standard washer and dryer in your house, so it's a pretty massive instrument. In fact, we sort of joke at Goddard that that instrument alone is bigger than a lot of the missions that the whole satellite that a lot of other programs have. The lightning mapper, which is basically just a giant camera. Then we have our space weather instruments. So let me just step through each of them. First of all, the imager. We're going up to 16 channels and making 3 times, that effectively is triple the number of channels. The spatial coverage is increasing about 4 times, and increase in temporal resolution about 5 times. From what does it look like? These are a lot of times I put a lot of charts in here just so people can take the charts and have them as reference. This sort of looks like at today and what's happened with GOES-R in terms of the spectral bands. You can see we've added another visible image and as well as 4 near infrared, and then added additional 5 more at the infrared spectrum. In terms of, again, this is mostly for reference. I wanted to highlight, when you look at the purpose of why we're doing this, you can see with the infrared, or the visible and the near infrared, we're getting a lot more in terms of the surface, in terms of aerosols. We're also getting a lot of better insight into the cloud, the phase, particle size. And then as you move up into the mid and long range infrared bands, you start seeing more with the fog. You get the water vapor. We've got additional water vapor, so instead of just having one water vapor, we have a high, mid, and low water vapor. The volcanic ash community, volcanic tracking has been really on us. We added some volcanic ash detection channels as well as silicon dioxide channels, and also for improved sea surface temperatures. So quite a capability in terms of what the bands can buy us, and I'll show a little more of their applications later. I briefed the FAA in terms of capability, so I just used a few of their charts in here. Here you can see off the Rockies some of the waves that you can see from the jet streaks as they come over the Rockies, and what the Aviation Weather Center is really excited about this because it really helps them with their turbulence and identifying locations of that. Looking at just the IR, again, from the aviation community, much more precision and only the cloud type heights and a lot of the constituent particles at that better resolution. But as an engineer, it's hard for me to get real excited about that stuff. I get excited about the coverage, okay? Because you always want to be faster than the previous guy, right? Well, this current goes in 5 minutes, you can see how much he can do. And I can, in 5 minutes, scan the entire hemisphere. Now, this is driven a lot by the Weather Service, because today, whenever the Weather Service wants to go into rapid scan, what happens is you lose the hemispheric look, and you get goes to 3 hours, and so the people with that big picture look are always troubled when they go into rapid scan. So what we're able to do when you can scan the whole disk in 5 minutes is we can go into different modes of scanning. So what we do is we do have a mode where we can scan the whole hemisphere every 5 minutes, but we've got one that looks like the Weather Service preferred mode, where we'll do a full disk every 15 minutes. And you can see from the blue box here that that's a CONUS, so we'll scan the CONUS every 5 minutes. And then we can also pick a mesoscale feature like a hurricane and do that 30 seconds. So we can do that 15-minute hemisphere, 5-minute CONUS, and 30-second mesoscale all simultaneously with the imager. So as we've presented this to the Weather Service, it's sort of mind-boggling how they're going to task this. The choice of the mesoscale features and that. We do have flexibility in that we could actually change the scan and slow down the hemisphere and the CONUS and do more if people find that 30-second has great value. And I just had that image on the right that just showed some some of that high temporal resolution imagery could do. I'll have a lot more pictures of that later. Moving on to the lightning mapper. Again, this is about as simple as instrument as you can imagine. It's basically a CCD with a big optics that takes a picture every 2 milliseconds. Okay, now it's a pretty cool. That's a pretty fancy camera. But so to get the lightning, we basically are just comparing each of the images and then trying to determine, counting the number of flashes that happen between each of these. This has been, to me, just a fascinating learning experience in terms of what Lightning Mapper is all about and what it can. So I want to start this off because when I started this, I had my visions of what lightning was, right? To me, it's that bolt that comes out of the cloud and hits the ground. I mean, that's all I think. But the research has shown that about 80 to 90% of it is all cloud to cloud. So the cloud to ground strokes are very minimum. But even a cloud to ground strokes, I wanted to share with you this. This is a 2-second movie of a lightning bolt. And I just find it fascinating as this is what's really going on. And look at the rate of this camera. A colleague in Brazil took the 7,500 frames per second to get this. But this, again, this is in 2 seconds, all this happens. And so this is the part we're probably not even seeing in real time, right? This is, you know, all this cloud-to-cloud activity. A lot of the yeah, it's all pretty fast. And then the part that we see, bang, that's all we see, right? But that's not the end of it. You know, it just keeps going and going and going. So the point is this lightning phenomena is actually incredible what's really going on up there. And where we first got our insight into this is NASA in the 90s launched the Tropical Rainfall Mission, and they had LIS, which is a lightning mapper from, although it's from low Earth, you do get some sense of this. So this was projecting some LIS data over some GOES imagery over the May 99 tornado outbreak. And what you notice when you start looking at this is that this is, again, a lot of the cloud-to-cloud lightning is being picked up that you're not seeing the lightning, the ground-based lightning detection systems. So all of this cloud-to-cloud stuff is very highly correlated to where the severe weather is. And so when you start looking at the flashes and where the severe weather was, there's a high correlation. So it led to a lot more research into what really you can take from this. And what the researchers down at University of Alabama, Huntsville have really found is that it's this total lightning flash rate is an incredible indicator of the physics of the cloud and the change and when change is happening. The graph on the left showing typically, if you just look at cloud to ground, that blue thing, it's pretty stable through severe weather buildup. And so there's not much signal looking just the cloud to ground. But when you look at the inner cloud with the cloud to ground, you can see that rapid increase in the flash rate before, you know, here is an example that had about a 20-minute lead time before a tornadic event. But so we put in, there's a number of ground-based high-frequency networks that can detect the cloud-to-cloud with about a 80 to 90% detection rate, which is what you need to really understand the phenomena. And so there's one around Huntsville. I put one in around DC because I live there. And the folks out in Norman, Oklahoma put one out there, so we have some data sets out around Norman. And then the Cape put some down there in around the launch site. But we're really collecting a lot of data from this. And what the folks at Huntsville did is they looked at an entire season of all all tornado warnings and severe weather put out in the Huntsville area, and they found that for every tornado that was warned, that this jump signal was occurring on average about 20 minutes, which was 7 to 8 minutes above the national average for tornadoes. But more incredible is that the false alarm rate dropped about in half, which I think is even more important to get the public to respond to this if you can drop off that. So again, this is not necessarily perfect science yet. It's still learning until we get this up flight and really work with the Weather Service. But what we've shown them to date, the severe storm folks are very, very excited about this. Here's an example of how we're looking at ways, how do you present this data even? So here's an example of just doing flash rates. I just caught a snippet here. But the lowest of these cells shows the 1+, so there was one cloud to ground strike is all it was. And each of the 3 cells there, you know, grew from this point. You can see the Weather Service warning there. The top one is actually became the Moore tornado. And on that event, there was there was a big flash density jump about 26 minutes over the first major hail event. So there's a good signal there. And about 19 minutes before the tornado formed, there was another big jump. So again, we see lots of potential here, lots of excitement in the community, but we're still learning to really how to use the lightning data sets. Moving on to our space weather. Did you count how many instruments I had? I've only got 2 looking at the Earth. And I got a whole bunch looking at outer space. So, you know, you could say that I'm more of a space weather satellite than a weather satellite, so I have to be careful. But I stole this chart from Berger out at Dr. Berger out at the Space Weather Forecast at SWPC, yeah. Because it's sort of it describes the environment. To understand why we fly these, you have to understand that. So the radiation, the energetic particles, the plasma coming out of the sun is a pretty nasty environment, and we ought to be thankful for our magnetosphere every day for protecting us from this nasty stuff. This chart didn't show it, so we had Goddard Graphics sort of do that. What does it look like as a movie? And when you think of a coronal mass suggestion and what it does to the Earth, it gets pretty exciting if you're sitting here from a casual observer perspective. So that major coronal mass hitting our magnetosphere is just wrapping fields around. It's charging with particles. You can and brings that charge right back to our atmosphere where it creates the northern lights. Hey, that's exciting. But there's a lot of other bad stuff that happens. There's a lot of radiation. There's a lot of disruption to our communication systems, threat to our navigation systems. It affects our satellites. So that's why SWPC exists, to really to monitor and do all that. And when I overlay the GOES orbit on that, you can see why we're in a nice position to really do a lot of monitoring of both the sun as well as the magnetosphere and the ionosphere around the Earth. So the first of ours, I'll step through these quickly, so I'm not sure how much interest in this is. We do, the current GOES has a X-ray imager. We're moving up into the ultraviolet region. NASA did this with their SDO mission. So the ultraviolet shows the surface of the sun a little bit better, and you can see from a lot of the dark spots where a lot of the solar wind's coming from, and the bright spots where we're seeing a lot of the active regions, so the flares and the stuff will come. So the SUVI is basically just every 10 seconds providing an image in 6 different bands of the surface of the sun to keep the forecasters aware of what's really going on. Then we have this mouthful of an instrument called the Extreme Ultraviolet and X-ray Radiance Sensors. I hardly ever say that. So that's what we call it, the EXIS, which is really 2 telescopes looking at the sun, which is actually trying to measure the magnitudes and stuff of the solar flares and the ejections, but trying to do it more with the photons, so you can probably get a few hour lead time before the actual particle masses reach the Earth. We're also we've got a whole suite of instruments on board that are measuring the energy particles around the Earth, so the ions, the protons, alpha particles. That is just raw data that then goes to SWPC that they use to model the Earth's environment, so they're just data collecting points for that. And then we have that lovely magnetometer. You know, what do you think the hardest thing about a magnetometer is to build? That crazy boom, you know? You got to stuff it in that little box there in the middle, sort of like a jack-in-the-box. And then it's got to perfectly deploy every time we take the lid off. And we had so many problems, because as you expand it, little things break, stresses aren't quite right. You vibe it to see if it'll survive the launch but things break. So you can see how happy everybody here was a successful deployment, lots of thumbs up and cheering when we finally got that to work. So the reason we put a boom, like I mentioned, you got to get away from the spacecraft, because a lot of electronics in the spacecraft will create signals that you don't want the magnetometer to pick up. We also have a lot of other payloads on there. We relay the search and rescue signal that picks up. We're just sort of a relay for that system. The Weather Service uses us to bounce, and it's almost embarrassing to call a high-rate information service when you can measure it in kilobits. But this is basically the Weather Service puts together imagery products and then use that to get it out to so for our low-cost thing, emergency managers out in remote areas can get raw, or basically imagery charts, data products, whatever the weather service wants to send, just from a simple receiver. And a lot of that is for redundancy, that they have that in addition to whatever other primary sources we have. We also do data collection system where we're taking a lot of water gauge information and other sites and pumping the data up the satellite down into our data processing system. And I mentioned before, the big kahuna here is the GOES-R rebroadcast, which is all of our raw data down and available through that. Since I am an engineer and I love hardware, I have to show you my baby pictures. So this is just a sample of all the instruments and the satellite in various assemble process. But that's always not necessarily exciting. So I had to not only show baby pictures, but bring my home videos too. So, you know, a lot of times this is the big assembly point where this core over here on the left is the propulsion component. That's built down at near Stennis. NASA Stennis, Lockheed has a facility that builds that. And the part that's being lifted here is built out in Newtown in Philadelphia. And they're brought together here in Denver where they're assembled. So the part coming down has all the electronics and the other one has the propulsion. So everybody complains that you satellite guys, nobody's ever working on them. So I wanted visual proof how busy it is in a high bay and how much work is being done. It is always entertaining to me when you look at the quality assurance guys in those chairs down there to make sure everybody else is doing their job right. So this is about an 8-hour period. You have the clearances on these are literally millimeters, so you really don't want to mess with that. But for us, this was a huge monument event last fall where we finally got the two major components of the satellite together, so that we could then mount the instruments on board. So, ta-da! We did finish it. This is, when you think of, we started this, the paper studies for this started, anybody want to guess? Well, you guys, I guess I should teach me to ask such a question. The first contracts for studies were let in 1998. Okay, thinking, yeah, but I'm sure it was going on before that. The first production contract for the imager was let in 2004. So that's the kind of time scales it takes and the colossal effort it takes to really pull all this together. Right now, so we've got it assembled here. Just this week, we're starting to test it. In other words, we're turning it on and making sure everything works together. So we sort of have our fingers crossed. But it's going to take us 6 weeks running at 24/7 to check out every, component to make sure everything works as we've designed it. So once we finish that, then we'll put it into our environmental test where we'll put it into vacuum and run it down to real cold temperatures, hot temperatures, thermal cycle it to make sure it survives the space environment. We'll put on a shaker and then rattle it like crazy. You know how nervous it is to put a $1 billion piece of hardware on a shaker that shakes it to death and hopefully nothing breaks? Yes, right. And then we'll do an EMI test. So that's what all we have left to do for this year, and we'll be able to be ready for launch. Now the ground guys, they always want their fair share. They're a little mad at me because that little thing you show up front, Dave, if you notice, we didn't talk about the ground. So I'm on their bad list right now because we didn't give them due process. So I have to at least mention this. This shows our facilities. So our NSOF, where we put all the equipment in, then the Wallops facilities. I want to point to one on the right. We put our backup up there in Fairmont, West Virginia. And this is the West Virginia high-tech corridor. And I can tell you, there was a whole lot of excited West Virginians when I told them we were going to go put 3 16-meter antennas on that ridgeline in West Virginia. Because they know that they are high-tech now and they can point to those and everyone prove it. I was a little concerned because the first request they said is, see that little silo in front of the building? They wanted me to put one up there because they thought that would be cool too. But what you don't realize is what looks to be a simple job is, what do you think is underground most of West Virginia? Well, it used to be coal. There's a lot of coal tunnels. And so when you put a large 60-meter antenna on a hillside, which had previously been mined, and you have pointing requirements looking at something 22,000 miles away that need precision things, well, we had to drill holes down many, many feet and fill it with cement slurry. So I think we increased the weight of West Virginia by many metric tons in this process as well. So now we've got a very, very stable place for those antennas. So here's the grounds baby pictures. We have basically all of it in place. We still have one 60-meter WALPS we've got that's currently in operation if current goes. Once we get the other 5 working and fully operational, we'll be able to tear that down and put the 6th one in. But the ground system is in great shape. I was telling Bill Apente yesterday, when we were laying this out in the mid-2000s in terms of the processing it took to actually move this data, because we're moving from 2 satellites, we move like 150 megabits per second through these things, and you got to take that fire hose, create your products, and get them out. You can't wait because that next, every second that more data pulling in. So the size of the processor that we were planning on was equivalent to NSEP's full processing capability in their supercomputer. So now he's obviously gone much beyond that, but it was just in 2005, it was very interesting to think that's how we were scoping our processing system. Just wanted to list our products here. Basically, when the program got started, we, as all big programs do, we sort of run into budget problems. Guess what was cut? Half the products. So I don't know why it always works like that, I guess we love building our hardware. But so this product list is fundamentally, other than the Lightning Mapper stuff, the same you see from GOES today. So the baseline products that will be just these same type of products with the higher refresh and all this. But not to be stopped. I couldn't stop at that. And I've worked on, in the 80s I worked on the DMSP program, and in the 90s I worked on POSE program. And it took 10 years and took a sabbatical from the satellite crazy business and went over to the Weather Service. Realized how even crazier that business was. So I came back to GOES-R. But what that time in the Weather Service taught me is how critical the link between the satellites and the forecaster really is, and how little energy is put forth there. So I committed myself to force the satellite reach community, which seemed to be stovepiped, to reach out and work with the Weather Service. So we implemented what we called our GOES-I Satellite Proving Ground, so that we would actually get out to the Weather Service and start showing and talking and doing things and getting feedback way before the launch. So we've been doing that now for about 6 years, and it's been just a fabulous success. I've put satellite liaisons or subject matter experts at a lot of the Weather Service national centers. I also put a couple of postdoc data assimilation folks out at Boulder to work with the high-res data assimilation, and then Norman as well to work on some of the mesoscale research, looking for ways to improve the assimilation of the satellite data products from GOES into the rapid refresh models. We've developed training. We were able to create all of the GOES products out of synthetic data. So with all the other data sources, we can actually replicate what GOES will look like and show it to forecasters to get feedback. And then we also were able to take WRF output. So we take the model output, and then we simulate what the ABI would see of that model output in 16 channels. And then we take that and run it through our product system so that we actually use the models to create what the GOES-R imagery. Now, some sarcastic people say, well, then why do we need to launch a satellite? You can just create all those great things right out of the models. We're still working on him. Other things that we've done is we've had a visiting scientist program. I basically, what this is I put out a notice that says any scientist who wants to go somewhere else and learn what they're doing and bring it back to where you are, I'll pay, 2-week 2-month trip. So I've had a lot of people take advantage of that. I've even sent some Weather Service folks over to Europe and some Europe scientists over here, and the learning back and forth is just phenomenal when you see someone that does business differently and how they use the data sets. So we've got a lot of good stuff that's coming out of the proving ground, and so I wanted to go into a little more detail. In terms of who is in the proving ground, this is probably a little bit busy, but from the satellite side, we've got our traditional cooperative institutes that we work with. With the Weather Service side, a lot of the NSEP service centers are on here. And we have a number of forecast offices. And what basically all those folks are agreeing to do is to work with our synthetic data sets, our proxy data sets, to understand them, give us feedback, and sort of get some buzz going in the Weather Service. And the first year I did it, I went and listened let me back up here. The Weather Service has hazardous, every spring they have the spring experiment where they bring the latest and greatest in. So we started participating in that. And so the first year I went out there and I says, all right, I want to hear this, how much they love me. And the forecaster's response was, well, it could be interesting. Yeah, that might be promising. It's a very typical forecaster, you got to show me, right? And so over the years have gone by. Last year when I went out, I saw the output of 1 week's forecasters, and it had, oh, these things show promise, this technology show promise, and oh, you could do this to this. And then it had a chart that said, I want in my office yesterday. And it said, goes 1 minute imagery and lightning data. So I think that just shows that in 5 years of working, how much we've brought the community along to get excited about what's coming down the line for GOES-R. Again, I guess I did talk to this a little bit already. We've created this synthetic product so they can actually see what ABI will be providing them. I also want to mention, as part of our test ground and proving ground, we've brought the storage satellite, GOES-14, out of storage and turn it on in what's called the super rapid scan. So we're actually, for a very small area, zoom in and get 1 minute imagery so that we can show all the forecasters of what GOES-R is going to be like. Now, GOES-R is actually going to have the capability of doing it at 30 seconds, so it'll be twice as fast, and it's going to be at ½ kilometer versus 1 kilometer of today, so they'll be even better than this. But as it starts out, the first time you show the forecasters, there's lots of staring, and the more you look at it, just the more you're learning from these data sets. So we've got more plans for 2015. As you can see here, we're going to bring GOES-14 out of storage and put it in Super Rapid Scan for the May to June for about a month. That'll support the spring experiment. And then we'll do out in August, and maybe we'll even catch a hurricane. But we've got some examples of the data sets. Now here's the great state of Wisconsin. You know, I don't know how that gets into my briefings, but on the right you're seeing your typical what you see in GOES today. And when you're looking at these convective environments, clearly it looks like a series of snapshots. It's really difficult to really see what's going on. But when you start looking at the convection and explosions at the 1 minute, it's just phenomenal. So here are the folks in Chanhassen outside of Minneapolis actually found this great for supporting their Minneapolis-St. Paul airport. So even though we're running this in a research mode, we do put it out in blogs, and we try to get people to look at it and start imagining how they can use this. Here's just a 3-panel. On the left is just your standard GOES. The center is actually when we go into rapid scan. And then the right is the 1 minute. So again, even with the rapid scan we do today, it's still rather jittery. And we're really moving to, you're almost watching real time, the convection and the growth, the clouds, the anvils growing. Just a tremendous amount of, I've reached my limit of meteorological vocabulary, I think. But the
super rapid scan awesomeness.
Super rapid scan awesomeness, thanks. So what that's doing with the convective folks, I think until we are up there and giving it to them full time where they know it's there and they can start to really figure out how to use this imagery. I know the Hurricane Center has been very, very excited when you look at this 1 minute imagery of Igor and you start looking at the eye wall and some of the bands and and the convective growth out there. It's just amazing the kind of detail. And again, think of this at twice this resolution and twice the speed is what's really coming. So this is going to be very interesting. This is actually Sandy, and we had it running during Sandy. So this is 1 minute imagery run through the full 6 days. Now this is the kind of thing that even I run these loops at my desk and just stare at them, because every time I look at it, when I look at the outflows and the bands and the other convective coming in, the caps coming in, the dry air impinging on here, I think, you know, we're going to have to, so when Rick's talking about his plans for 16, and I'm thinking that you're going to have this in 16, I think we still have a ways to go to even imagine, you know, there's got to be ways, you know, here you can see where the dry air is as it hits the coast and it sort of broke up, but the amount of data information in this is just overwhelming. And we do have all of the Wisconsin site that we sort of run this out of, keeps all these data sets on their website and their blogs, so it's always available. We put some on our YouTube site, so there's a lot of this. And again, this year we're going to be running this a couple more times, so get excited about this. What did you call it, Dave? The eye candy. Super rapid scan awesomeness. There we go. New words in my vocabulary. Now, here's an example where we took some of our 1 minute. This was that derecho event out in D.C. back in 2013. I think I was out camping with some Boy Scouts when this came through, and I got word of it and actually ran to the head of the camp and said, "We got to get these boys out of their tents into the safe." And he looked at me like I was a nutcase. He said the Weather Service hasn't issued enough, and I said, "Why not?" You know. But we actually got the boys in when the wind started picking up, so we're a little bit late. But this is an example of with your 1 minute imagery, you can see the large, but you know, since it's derecho, you're not seeing the explosiveness. You're just seeing the movement. But when you start putting the flash density of the lightning, you can see where the severe components are, even through the heavy clouds. And the two red lines there are actually two tornadoes that happened in that event. So again, you can see the correlation between the tornado events and those high density lightning flashes. So again, this is an example of a way to try to show the information that we're going to be able to do. This is an example. One of my satellite experts at HBC actually just sort of did this on the fly, saying, "Hey, look at how we could do this." Those of you who are familiar with the motion vector winds, the major input we have in models today, and because satellites can give good temperature and moisture profile information, but we can't get a direct measurement of wind. So we basically track the cloud motion to create the wind vectors. So we've upgraded the algorithms to take, but the requirement I've been given, you have to work on this one, was only for the 15-minute. So this is what we built today. Still, we're getting 3 good layers on this, so I think we'll see a much better insight in terms of the impact of these models. I wanted to put this in because we had the super rapid scan in the fire weather community. Here's an example where even today's fire weather thing, when you got the 1 minute modes, the incident commanders are very interested because here not only is it picking up the hot spots where the thing is, but you can immediately see the plumes from the major fires expanding out. So if you can think of yourself as an incident commander on site and having real-time access to this, they see that as a tremendous aid to their situational awareness and understanding of how to put the firefighters, keep them out of harm's way. I'm so tired of people telling me that GOES can't see Alaska. So I had to do a reprojection of what Alaska looks like from GOES. Even though the resolution is a little bit poor, it's amazing that you can still see even the North Slope. And from certainly from a synoptic scale and a motion, you can see a lot of the activity up there. This is a result. This was sort of a guilt trip. You know, I worked in the Weather Service, and all the technology we put out, I don't know if you know the deep dark secret is, we do a great job for pretty much the high plains and get everything working there. And then it's so late that we just rush into operations, and the poor mountainous West and Alaska and Hawaii they always got to fix it to make it work for them. So when I took over this job, I says, I'm going to do something for those poor guys in Alaska and Hawaii. So I took all my researchers up to Alaska, Hawaii, and got them integrated and started working. And actually, that's where we did the first started solving their problems in terms of applying satellite data. So I feel like I assuaged my guilt from the Weather Service a little bit. Yeah, there's Diomedes right there, yes. The another sort of aside, so we have the Institute up at the University of Alaska in Fairbanks working very closely with the service. So they've joined us and helped with our proving ground stuff. I was trying to do a similar thing in Hawaii, but we couldn't get a researcher that was a real good satellite guy to Hawaii. Can someone explain that to me? Well, needless to say, my solution with this, I went up to Wisconsin and I offered a grad student, hey, I'll pay your travel to Hawaii anytime you want to go if you go help the Weather Service there. So I made a very happy grad student in Wisconsin who has spent many weeks helping out the Pacific region get satellite data better into their operations. This is a product we have today. Again, this is an example of our synthetic data that we created from the WRF model. You know, to me, it's just a pretty picture. The Aviation Weather Center, this is to them a very phenomenal product because from them they're getting they've said the upper structure, the particles of the top of the clouds, and it really helps them with their aviation forecasts and stuff and understanding what's really going up at altitude. We have our typical precipitable water vapor. And here's an example where the satellites have never done really, really good in total water vapor. So this is an example where we do our best with GOES, but we also then combine it with the microwave out of the polar and also ground-based systems. So we're trying to work with reserves to create a multi-sensor precipitable water thing. And that's really the wave of the future. I mentioned when I took over and got the proving ground started, I said they're a bit stovepiped. The weather service, or the satellite guys kept too much just doing stuff with satellite stuff. So the energy now is much more into looking ways to blend these things together. I mentioned the volcanic ash. We got a couple of additional channels. I put the examples of this unpronounceable Icelandic volcano, who, if you recall, when this erupted, it basically shut down aviation throughout Europe. And it was because they didn't really have the ability to understand really where that ash cloud was going, and their model was rather coarse, and so they figured that the ash cloud is going to take over Europe. We had actually been doing the GOES-R volcanic science. We had been running our algorithms because we're basically, our products are to do cloud extent, ash type, altitude, so we really can define that ash cloud very, very well. And so we were running it over Europe because we were using the EUMETSAT satellite because they have 12 channels, and the channels that we were planning to use GOES-R. And so when the Volcanic Advisory Center in London found out that we were doing this, they asked us to ship these, and they immediately then revised downward that and got things going because of the precision that we were able to provide them. So we're actually making an impact operationally even in the research stage. So I mentioned that those are our baseline capabilities, but we wanted, through the proving ground, to really push things and get people to think about what could be. I mentioned, this is my challenge for the Hurricane Center. This is the requirement I have on the left. This is just the low altitude, 15 minutes. well, what we've done with the scientists is we've actually done it down to on the 1 minute imagery, and just a phenomenal explosion in the vectors and what we can do with that. So I'm assuming that some point we'll have this. Probably for the forecaster, there might be some value to this. It'll probably be a while before you guys can assimilate at 1 minute, but it's probably one of our challenges. But certainly for the science, we have moved it, and you can just see what, and so imagine 30 seconds, because when you have smaller steps, you can really find the continuity between the aerosols and really know which one is still there. The farther in time you spread them out, the more uncertainty there is in the particles. I got a lot of charts here. I'll probably skip through these really quick. One of the things that the FAA has been very interested in, as well as the Weather Service, is really to improve fog and low cloud. So we've both, from an observational and a predictive thing, we've got a number of things. On the predictive side, there really wasn't, we couldn't find a good definition of what fog and low stratus is. So we basically used the FAA's flight rules. So we used the VFR and IFR definitions to try to do predictions of when those conditions are met. And again, this is the wave of the future. You can't just do this with the satellite, but you got to take that satellite data, combine it with surface data, sea surface temperatures, numerical weather output, bring all that in, intelligently combine it, and then create your probabilities for fog and low cloud. So we've been doing this. Again, it's the GOES-R scientists that I push beyond out of their box, if you will, to go look at where we can make a difference. And we've made some good work going on here. Here, just from an observational sense, is what it looks like. If you can see on the left, the Weather Service's here, or the GOES fog product that we were putting out of GOES, is this thing on the left. Now, I don't know how that's useful to anyone, but even that rudimentary of an image was helpful and desirable. Just applying our new algorithm to current dose brought us to the central thing. That just shows the science improvements we've achieved. And then the third panel is, well, we project once we get it into the GOES-R era with a better spatial resolution, and that we'll be able to put out an observational fog product that looks at it. And so clearly you can see the valleys and river valleys and that, which I can't, when I look at the left, just a dramatic improvement in this. So certainly the Weather Service folks who have been involved in this are very excited about this fog capability and how it can help, primarily for aviation and aviation operations. And then for the predictive thing in terms of IFR, here's just an example that we put together of what the predictive element, for IFR conditions would look like. So again, I'm not saying it's a perfect product, but it's just an example of trying to give a predictive tool that's multi-sensor in nature that we can give to the forecasters so that they can predict when clearing will happen and where the fog will happen. Now, I put this chart in only because Louis Ucciolini sent me this chart. Because he was so excited because he went over to the FAA and they had been working with us in the proving ground in this fog product. And here's a case where that better precision on a top circle, even though it's colored yellow, you can see there was a pixel that was still cloudy, or the fog. You can see that on the right, and then a short time later on the left, how clear it is. But the sense that that precision let him know that it was coming, that it was clearing was coming up, really led him to move airplane operations much faster than they would have. So Louis was getting all these nice things from the FAA, which I guess is not a common occurrence. So he made a point to let me know that it was a very happy point for him. But so again, these are examples where I think we're going to make an impact in operations and help the Weather Service in many parts of the nations. Another experimental thing, and this is, we call it the RGB, or red, green, blue. We've only got 2 visible channels, so we don't have true color. But when we did the scientific exchange, we sent one of the Weather Service guys over to Europe, and he brought this back because this is actually being used. About 80% of the satellite use is in this RGB. And basically, all you do is you pick whatever channels you want. Pick 3 of the ABI channels, and then just project them. But you can pick whatever channels you pick, gives you different pictures and features. So for this one, it really highlights a dry air mass above and the moisture laden air mass below. And so this air mass product when you look at from a hurricane sense in terms of steering currents, it gives a much stronger visual of what that is. The problem is you can see so many features, and so you can combine so many things. It's sort of like the infinite permutation problem. So for forecasters, it's awful because you give them too many opportunities. So we're really struggling of which of these RGBs might be valuable to forecasters, and then how we train the broad things, because interpreting things we've found when we've tried to bring some forecasters in is a real challenge to get them to understand everything that's going on with these RGB projects. But another example we did is for low cloud. So I guess you really good meteorologists can see the dust and the cloud separation on the in the left there, right? Can you? Well, let me tell you, if you put a different channel into RGB, what it would look like is that. Is that a little better? So, I mean, that's just an example of how you can really pull out features with the right combination of channels. But again, the opportunities just are so great. We just have a lot of science work to do once we get this up to really say what problems are we going to solve with the Weather Service, which ones are of the greatest value. Here's one that is another great example. And again, I highlight here because I've got the satellite researchers doing multi-sensor focus in. Now here's one where severe storms, initially we put out sort of like a black box convective initiation. Yes, no, yes, you know. And the forecaster said, get out of here. We don't want to be told yes, no. We want to understand what's going in it. And so out of those discussions came out this probabilistic forecast for severe storms. And so if you look real closely here, you'll see that sort of pink circle in there. That is the algorithmic calculation of the probability of severe weather occurring with that specific cell. And if you run your cursor over it, like we did in this screenshot, and you can, I don't know if you can read it very there, but that basically is telling you all the components that led to that assessment of probability of severe. So in this thing, you know, you've got icing, you've got the radar mesh component, you've got vorticity, glaciation, and that gives you numerical values for all those points. So the forecaster can then see that and then immediately get confidence in what the algorithms are telling them. So what we found in the early things is they like to ignore it, and then when it hits about 50% severe, they'll start paying attention to that cell. So this is an again, so then I just sort of ran this one to show how it over time might grow for a cell. And then you can see the Weather Service putting out their warning boxes as that thing progresses. But again, this is, again, it's sort of where our satellite researchers are. Now we got to take this, work more with the Weather Service, figure out ways how to implement it and really get this worked out. But again, I think it's a real good sign of where the future's going in terms of the integrated multi-sensor capability. I showed you the RGB products. Here's another one we got from Europe. And it's the funniest name. They call it the sandwich product. And I go like, why would you come up with it? I said, we need some PR help, so you guys can maybe help me out here. All this is basically taking a baseline product, which I guess is the bread, and here we just use the visible channel, so you got the visible cloud, and they overlay another product on top of that, and here that was the RGB of a cloud top pressure. So when you do that, you're basically, again, pulling out features from that for a visual view. But again, when you start looking at the combination of this, and you look at the sandwich, or you look at the sandwich products, potentials with the RGBs, it's just an explosion of possibilities. There are a lot of work is still coming in terms of what to do with this. Now, some of our other folks started combining another look at it in data fusion is if you start looking at here you got the visible and infrared views, but you start combining it with the lightning strikes, the overshooting top detections, severe weather reports, and you start to draw all these things in and giving the forecasters a real sense. So we've gotten some positive sense over this type of work, but again, it's an area of interest, and the Weather Service is really looking at trying to build it into their decision support system. So we're sort of doing some of the basic research and sort of pulling this all together. Again, I grabbed this out of the Weather Service only saying, you know, their vision is to really bring their next generation warning system online. That really takes a lot of these products, combines them, and presents their forecasters with a great opportunity to understand that. So I think this is still a lot of exciting stuff's coming, and a lot of exciting potential we're building the case for. A couple other readiness things I wanted to bring up. I told you about my visiting scientist program, where I send people wherever they want to go to collaborate. Well, that spring experiment I mentioned last May, I actually funded 4 broadcast meteorologists to go out there and spend a week in Norman. And the feedback we got was phenomenal. One of the broadcasters said, hey, this is the best training experience I've ever had in my entire career. To see the latest and greatest technologies being brought. We got a real life.
My colleagues went. She loved it. Erica Grow.
Yeah, okay, I had a quote from her, so good. First-hand experience, excellent. In fact, she gave me the picture right down there. So again, we got that coming up this year. Again, opportunities we'll gladly bring you in and see the latest greatest of all technologies into what's happening. Also, the AMS Conference on Broadcast Meteorology this year, I've put into the AMS approval to actually run a short course for on GOES-R for broadcast meteorologists. Now, it hasn't been approved yet, but I can't see any reason why it wouldn't be. So your advantage there, instead of having the engineer program manager talk to you, you get all of those special scientists who are doing all this great work to really give you the nuts and bolts of what's going on. So I think this is a great opportunity to even get into more detail of what's going on with GOES-R. A lot of you get the data through various vendors. To support them, what we've done is we've built simulators of what the GOES-R data stream is going to look like directly from the satellite. We built 4 of them. I finished that in the late 2013. And they've been available to check out by vendors so that they can test their antennas and their systems to make sure they can process it and do all that. And they've been checked out continuously for the last 1.5 years. So very active community in terms of getting ready of all the direct downlink readout. I put this chart for completeness, but we have been working with Weather Service on a lot of training for GOES-R. So COMET, ShyMet, and Visit out at Colorado State, Sport down in NASA Marshall down in Huntsville, all have great sites where we've put a lot of this training, and certainly available for all of you to go in and go through any of the material you want to bone up on any part of the program. And then I learned that you guys, advertising is part of the business, right? So every couple of years, the NOAA has its own satellite conference. So coming up this May, if you want a whole week of everything satellites, this is the place to come in lovely downtown Greenbelt, Maryland. So if you or any of your colleagues, help get the word out, this is a place to really get into the nuts and bolts of a lot of that.
Nice visitor center.
Yeah. So anyway, that's all I really had. We've got a lot more data. We do run the Facebook at NOAA Satellites for our Twitter. Our YouTube has a lot of these videos, so you can always go there and have lots of good videos and a lot more photos on the Flickr account as well. A lot of these links are on the GOES-R website, so I look forward to continue engagement with you, and I hope you get a little bit more excited because we are excited about delivering this capability for the nation. Thank you very much.
Great, thank you. Okay, Greg, I'm sure we'll give you time to take a drink or two, and again,
anything other than water you got?
Just have some water. Raise your hand, and we'll bring microphones to you, and then you can ask questions in order. Craig?
Hi, Craig Setzer from Miami. Very nice presentation. A couple of questions. Is there a SAL or a Saharan air product on GOES-R?
Are you what?
A Saharan air layer product like the Meteosats have?
I'm not. No, the list I have is anything beyond that basic list. We're going to have to work with the Weather Service in terms of putting it in. So that I would put that in the next step type of thing. So we really do have a basic set of products. Again, I mentioned what happened in the early stages when cost cutting comes. I think they figure that if they cut that, the good stuff will come back, and I think that's sort of where we are. So I'd say no is the direct answer.
Okay, and then just a quick question: where does the scatterometer satellite mission stand these days, ocean wind retrieval?
There's not any activity. I mean, what's happened is GOES-R and JPSS have sucked in so much money. Everything else has sort of been very difficult. So even Jason and Discover have trouble to get going, so we've got them going. So as we go through all this, I think what happened is when NPO slipped so much, if you look at the massive investment to develop these systems, you know, the polar system was supposed to be in the 90s, then GOES was going to be in the 2000s. What happened is that program slipped back right on top of GOES. So right now, if you look at the NOAA expenditure on satellites, it's probably at like $2 billion a year. No one likes spending that kind of money on it. So it's very difficult to do this. So until these programs come down, I think that's when the opportunities like that. But we're exploring different ways to get up. You know, perhaps we don't have to build a great big government systems. You know, can we build the instruments and look for other satellites to fly down? So we're looking for that. A lot, you know, some of that stuff we've got to look internationally and see how we can partner, like the Jason. So we continue to look for, and right now we're looking in those approaches. We're really trying to run the gauntlet on what we can do in terms of delivering that different approaches.
Hey, Greg. Paul Goodlow with the Weather Channel. A couple of questions on the Lightning Mapper. Did you say the resolution was 8 kilometer?
Yes, about 8 kilometers.
How often will that data be available? Every 1 minute, 5 minutes?
Well, think of it, it's a continuous data flow. So we're getting measurements every 2 milliseconds. And so as the data is flowing down, we have to keep, so we're combining it, and we're looking for the optimal ways to do this. So right now we see these jump products. So we're looking for flash density. So we'll be putting out just a continuous flash density. Now we realize this is like one of the most perishable data sets. So we've got to get that data set to the hands of the users literally in seconds for it to be of any use. So, you know, certainly with the Weather Service, we're working the ways to do that. It's just a matter of the comms and getting it. But it's not a very high, it's a very low bandwidth type of data set.
Will you have a distinction between cloud to cloud and cloud to ground in that?
We can't tell the difference from the satellite because like you saw from the Liz, all we are seeing really is those flashes in the clouds. So all we really are seeing is lights going off, okay? Now, we're combining it with the ground-based systems, so in a sense that will be available. So you got to sort of merge those data sets, and so that I would say is where you subtract it off, and then the rest is the cloud to cloud.
Joe Murgo from WTAJ in Pennsylvania. Paul asked part of my question. I had kind of two questions and a little follow-up question to that. Do you think this will replace the National Lightning Detection Network?
No. No, we see them as very complementary. I mean, again, all we're seeing are these flashes on the top of clouds. You know, the precision and the location and all that you're going to get from the ground-based systems.
Okay. And secondly, have you started to have conversations maybe with our vendors? Is all this new high-resolution data going to cause issues with bandwidth of us getting it out to us and to the average person?
I believe there will be a challenge there, just like when Dave was loading this up. You know, it's one of those things where, you know, most of my energy to date has been working that with the Weather Service, and so the Weather Service is under a major, you know, bandwidth expansion, their WANs and the NOAA port to make sure we can move all that. We're having to look at what are the smart ways, because you can't just move all this data everywhere. And so we're looking at ways to take, okay, for these small data sets that we can move normally, it's okay, right? And not have to take the whole thing. So we're trying to figure out how do you smartly make packets available so that people can just come in and grab the smallest data sets possible. So that's the kind of, that 7-day rolling archive I mentioned, we're building that in so that you can pick and choose and grab and pull the data a lot of different ways. The availability of that is probably a bit restricted, so I think we still have to work through that. But certainly for the broadcast community is the one I really think we got to do a lot of work in exactly that. I've talked with the UCAR about how, for the academic community, for example, how can we like create a mirror site of all these products such that it doesn't put a full load on maybe the NESDIS servers and have maybe some other sites. You know, perhaps we need a similar type of thing. But I think we're in that thinking stage right now.
Okay, it's Rick Knabb. Craig, I have a couple of quick follow-ups to your question. We've been going through the GOES-R proving ground at the Hurricane Center. The RGB color combination will give us a pretty decent view of the Saharan air layer. So that's one way I think we'll be able to get at that. And then secondly, with regard to ocean surface vector winds, follow on to QuickSCAT, there is the rapid scat that's on the International Space Station, and that data is starting to show up on the web, processed by NESDIS, and we're working on getting that into a more automated way into our operations. So and there's also the OceanSat. So there are international missions on ocean surface vector winds. So we're not totally in the dark on those two fronts.
Thank you.
Yeah, Greg, thanks. Dave Titley from Penn State. Great to see you again, and great presentation, Greg. First, I would just ask...
I miss you being a boss, you know.
Yeah. Please pass on to the NPOS guys that you can see Alaska just like Sarah Palin can. And because that is a major reason why they continue to fund VEERS, which nearly, as you know, not only broke the program, but nearly broke NESDIS, NESDIS and NOAA in the process. Had I known what you just showed me, I would have just shut that sensor down right there.
Well, I've shut down their advertisements when they say that.
Yeah, no, I'd shut down the sensor and save the money. And then we could do things like scatterometry. But the other part, the other part I have is I would just like to publicly say kudos to you and the GOES-R program, because NOAA takes so much you-know-what on their satellite management. And this is really, I mean, this is as complex as it gets, and you have been able to maintain a great working relationship. I mean, you're basically still on the same schedule you've been on for years now.
It's basically since 2007.
And you're delivering. So, you know, I don't think you or NESDIS or NOAA get enough credit for what you've done. So I'd just like to say thank you for
Appreciate that. No,
and finally, what this reminds me of is like building steam locomotives in the 1940s. It's the epitome of a great technology. But if it takes 10 years to go from contract, or 12 years to go from contract to launch, we're going to have to do better.
Absolutely.
So how you go on to disaggregate it and start working at getting those timelines down by years and years, so that we can bring newer technology in much more quickly.
Yes, that's we are looking at those various ways, and that absolutely.
Thanks.
Thank you.
Hi, it's John Morales from WTVJ in Miami. So along those lines, and with all the cost overruns over the years and so on and so forth, are GOES S, T, and U really happening? I mean, by 2019, is all this in line to occur?
Yeah, one of the advantages that when Admiral Titley says we have the advantage we've had of every other program is, I was given the mandate to buy 4 from the get-go. So what I did is basically bought the parts and all that. So right now, my S instruments are done. They're done, except for the GLM, I've still finished that. The rest are in storage. The T instruments are pretty much in testing. So in the next couple of years, all instruments are all 4. So it'll just be a matter of bringing the spacecrafts along. And the S spacecraft, so I showed you the assembly of the R spacecraft. The S module that has all the electronics is being built up right next to that right now. So I have bought phenomenal, the major portion of all the hardware for the 4 systems. And it's just a matter now of assembly and testing all the components. So everything is on track.
And a follow-up, beyond GOES-U, let's say.
Right.
What about this idea, and again, this was something that was presented to us a couple of months ago at IceWig, what about this idea of quite small satellites, each containing 1 or 2 instruments, and having an entire constellation of smaller, easier to develop and launch satellites out there?
Well, the Polar program is actually looking at working with MIT Lincoln Labs on that for the microwave. There's the CubeSat. They're pushing that proponents, right? From GEO, I still have the optics problem. I mean, the optics it takes to see 22,000 miles with any kind of precision. So the navigation, the pointing, and all that, it's hard to do that small. I mean, if you look at the focal plane for so the ABI is washer dryer size. Do you know how big the 16-channel focal plane, there's 3 focal planes are? Oh, it's small. Do you know how big my mirrors are? I got 2 mirrors, each about a stop sign shape, right? And then the lenses for the optics to, you know, be able to gather the light and bring it in. So my problem is I don't know how to shrink that from a geostationary. Now, one could suggest, well, can you just do, you don't need the geo if you have a whole mass of stuff at low Earth, right? So I think people have looked at those kind of things, and there's still, you know, that's certainly at a concept stage. I haven't, other than the microwave area, I haven't seen a lot of specific activity. But interesting enough, both NASA and the DoD, when they've done the disaggregation studies, one of the things that I've found, and GAO just published a report on this as well, is deaggregation does not save money, which was startling to me because I thought that would be a very quick thing. It does allow you to get the technology in faster. It provides more opportunities, more robustness. But, you know, because I figured, heck, I don't have to, if I don't got to spend $250 million on a rocket, that saves me a lot of money. But that wasn't the findings of their studies. So NOAA looks at it from a savings thing. So we still have a lot of work to do to find out what way to do it. But that is where that next generation dialogue is right today.
Greg Howard Bernstein, WUSA TV, and Erica does say hello. A couple of questions. You already have your rocket paid for and scheduled that's going to launch this, and as a follow-up, you know, as the private industry, SpaceX, those sort of companies come in, is that going to make it easier for you guys to get birds in the sky?
I hope so.
And okay.
Yeah, so I bought the launch vehicles for R and S, or you know, it's still I'm on the you know, monthly installment plan. So we've probably paid most, you know, 70% of the R vehicle and about 10% of the S launch vehicle. So we're on, but they're on contract. I still have to go on contract for the T and U. So yeah, I don't know who's watching, but man, I would love if we could get those available to take me up, because
competition may help your cost.
The cost that, like I said, I spent about $250 million on that launch vehicle, which is just eye-watering when you compare it to what SpaceX is advertising for those kind of things.
All right, other question, real simple. How big is this satellite? The size of a bus, or can you give us just an idea of the physical dimensions of this thing?
From the, let's go back up a lot. The bottom of the adapter for the launch vehicle to the top of the ABI is about 20 feet. If that 5.2 meters, I think it was the actual measurements. Yeah.
That's cool. Is there anybody else that has any other questions? Because what we'll do is, first of all, Greg, thank you again for your presentation. Take a sip.